Hey everybody, I'm going to take a few minutes here to go over an example that's very similar to the elliptical extra credit project you guys have. So if you notice this diagram right here, that's the exact same diagram you have on your extra credit. It's simply a sketch of an ellipse. This is the center of the ellipse. Here are your vertices. So the distance from the center to a vertex here is simply A. It's labeled on this side, but don't forget, it's also here. The distance from the center to the endpoint of the minor axis is B. We don't know that yet. We don't need to know it yet, but we will need to know that in a little bit. And then the distance from the center to the focus is C, but don't label that C yet because I want a different expression to put in these boxes. And really this project is sort of a combination of manipulating equations and some simple geometry. Perihelion is the closest distance the planet gets to the sun. So that would be this distance right here. And aphelion is the furthest distance between the planet and the sun. So that would be this distance here. Something else to know, 1 astronomical unit is approximately 92.9 million miles. I think that's the average distance from the Earth to the sun. We call it 1 AU. All right, so the first question here, it says, use the eccentricity formula to represent the distance from the sun to the center of the elliptical orbit. Your eccentricity formula, I'm really hoping you know at this point, E equals C over A. Okay, but I don't really want that form of it. I want this to be in terms, C in terms of E and A. So what you have to do is simply take that formula and solve it for C. Okay, I'm not going to do that work for you. It's pretty simple, but you need to do that. Once you get that value for C, you then take that and place that up in your diagram in those boxes. All right, so again, this is not going to be C. It's going to be a simple expression involving E and A that you'll put in those boxes. Okay, so now it says derive the formulas for RA and RP in factored form. So RA is the aphelion distance, and notice here's RA. Well, how do you derive that formula? This is where the simple geometry comes into play. This distance here is represented by what you put in this box. This distance here, remember, is simply A. So to come up with your RA formula, it's going to be A plus something. And then you're going to factor it. And you simply factor it by taking out a GCF. All right, again, I'm not going to do that for you, but that's how you come up with it. So now RP. Okay, well, how do you get RP? Well, RP represents this distance here, just that. Well, here's what we know. This total distance is A. This distance here is whatever you've got in that box. So to find the difference, you simply take A minus this. So your formula for RP will be A minus something, and then again, you're going to factor that by taking out a GCF. So you have two very simple formulas, one for RA and one for RP. Okay. Now, the next question here says, if the eccentricity of Venus's orbit, so your project obviously talks about two different planets, but for this example, we'll talk about Venus. So what do we know? Eccentricity is 0.0068, and the RP is 0.7181 astronomical units. Find Venus's RA. All right, well, again, this is just formula manipulation. What do we know? Well, I'm going to take my RP formula, all right, which is A times 1 minus E, and plug in what we know. What do we know? Well, I know what E is. Okay, well, E goes there. I know what RP is. Well, that goes there. Then we just solve this equation. All right, so I've got 0.7181 equals A, which I don't know, times 1 minus 0.0068. So A will equal 0.7181 divided by 1 minus 0.0068. I try and leave all the calculations for one step so that we don't introduce any rounding errors. And if I throw that into my calculator and round to 4 places, I got 0.7229. Okay, well, great. I still haven't found RA. Well, now I take my RA formula, which is A times 1 plus E, and what do we know? Well, I've now found A right here, and I know E from the problem, so I just have to plug those numbers in. So RA is going to equal 0.7229. And I still have all this information in the calculator. So again, to avoid rounding errors, hopefully you still have that number in your calculator. Don't round it and retype in 0.7229. Just take your last value and then do times 1 plus 0.0068. And again, just throw all that into the calculator. And for RA, I got 0.7278 to the 4 places, astronomical units. All right, so I just found the RA. Circumference of an ellipse. Mathematician Leonard Euler derived a close approximation of the circumference of an ellipse with the following formula. P, kind of like perimeter, but stands for the circumference of the ellipse, equals pi times square root 2 times a squared plus b squared. So a is the major pole, b is the minor pole. It says, using the above formula, find the circumference in AU of the orbit for Venus. Okay, well, let's start with this formula. P equals pi times square root 2 times. So what I need to do here is I need to find A and B. Well, we know A, all right? We found A before. Remember, for Venus, A equals 0.7229. So I can put that in here, 0.7229, and I'm going to square it. Plus, well, I don't know B. All right, so I need to find B. To find B, we need to use our c squared formula for an ellipse. C squared equals a squared minus b squared. Now, we don't know C either, but we can find it very easily. Remember from the first page what we said about C. It's whatever you have written down right here. Hopefully at this point you have C equals EA. So now I can come back here and say, all right, C equals EA. So for Venus, C is going to equal 0.0068. That's what we got for E, the eccentricity. It was given to us, times 0.7229. So if I do that on the calculator and go out a few decimal places here, C is 0.00495. So now I need to take that, plug it in here for C, use the value I already know for A, and we have to solve for B squared. All right, once I get B squared, I can put that number right here. I don't need to square it because it's already B squared. Remember, this is really A squared plus B squared. Okay, so let's do that. 0.00495 squared equals 0.7229 squared minus B squared. So I'll just subtract 0.7229 squared from both sides. I end up getting a negative B squared equals negative 0.52256, and obviously just make those both positive. So now that is B squared. I'm not going to square this. I'm just going to take this value, plug it in right here. All right, so 0.52256. And then we just need to throw all of this into the calculator in one shot so we avoid rounding errors. And I did that, and I got 4.54206. And again, you want to go out several places because remember, this is an astronomical unit. And we're going to need this result on the last problem. Okay, so there is the approximate circumference of Venus's orbit. The last problem here, it says, if it takes Venus 225 days to orbit the sun, find its linear velocity in miles per hour. All right, well, how are we going to find linear velocity? That's simply going to be the distance it travels divided by time. Okay, so my linear velocity, the distance it travels from the previous example, 4.54206, what? Astronomical units, divided by 225 days. Well, this wants the linear velocity in miles per hour, not astronomical units per day. So I need to do some conversion factors. All right, first one, how do I go from astronomical units to miles? Well, I need one astronomical unit in a denominator to cancel with that. and I have to go back to that cover page, and 1 AU is 92,955,807 miles. So now I'll have miles in the numerator, which is what I wanted. And then my last conversion factor, I have to convert from days to hours. So I've got 1 day here, and then obviously 24 hours. And the days will cancel, and what we have to do now is finally multiply that times this, divided by this, times that. So you can create a fraction if you want. Just make sure if you put both of these in the denominator, use parentheses. I'm going to let you guys do your own calculations. But for a linear velocity to the nearest mile per hour, I got 78,187 mph. All right, so hopefully this example kind of helps if you watch this a couple times and then apply it to your project. Obviously, the formula manipulation is not going to be exactly the same as it was here, but you should have a very good idea of how to start that and go about finding those for the 2 planets you need to on your project. All right, don't hesitate to reach out, guys, if you have any questions on this, and good luck completing it.